Today we're going to be going through the Unit 7 notes on VSEPR, which is valence shell electron pair repulsion theory. This is also covered in the CK12 online text in sections 8.1 to 8.15. First, we're going to talk about bond dissociation energy. This is the amount of energy that is required to break the bond between two covalently bonded atoms. For example, I could have carbon bonded to another carbon. The amount of energy that it would take to break that bond would be 347 kilojoules per mole. As I increase the number of bonds, so say going to a double bond or to a triple bond, the amount of energy that is needed to break those bonds is going to increase. But there's something more interesting present within these numbers. If you consider that a single bond is about 350 kilojoules per mole, then I could say that two single bonds would be about 700 kilojoules per mole. So you would expect a double bond to be around 700, but it's actually around 660. So this shows that the second bond that is made between those two atoms, the second line, is not quite as strong as the first one was. And this is a concept that we'll get to a little bit later in the unit. Resonance structures are a type of Lewis dot diagram where it actually resonates between one of two possibilities. So for example, if I were to make ozone and have all three atoms follow the octet rule, I will need a double bond, but who's to say which side that double bond is on? I could draw it on the right, or I could draw it on the left. So early chemists thought that you could actually resonate between those two possibilities since both of them were just as likely. But the length of a double bond is actually shorter than the length of a single bond. So now that we can actually measure the length of these bonds, the molecule would be kind of lopsided. But what we see is that the molecule is actually completely even on either side, and the length is about the length of 1.5 bonds on either side. This shows that instead of having a real resonance structure, it's actually some kind of hybrid between a single and double bond. Now, even though resonance structures are now known to not be completely true, we still use it as a model since it's easy to understand and since it still follows the octet rule. This is another example of a resonance structure. So you don't have to flip between two possibilities, it could be more than that. And in nitrate, which is NO3 with a -1 charge, the double bond is actually flipping between three different possibilities. So it could be any of these potential forms at any given point in time. Just like with the previous example, in actuality, resonance structures don't really exist. Instead, we have about 1 1/3 bonds on each of these sides. Alright, so in class, I will be giving out styrofoam balls and asking you to make different models, trying to figure out how they would come together by spacing out the atoms as much as possible. So with carbon dioxide, you would have a carbon on one side, a carbon in the center, with oxygens on either side. So you'd end up with a bond angle of 180 degrees. And everyone always gets that one right. But when you start putting together the other models, it starts to get a little more complicated. With boron trifluoride, a lot of students will make their model look like this, where you have two of them in line and then one on the top. When in actuality, if you measure out the bond angles here, you have 90 degrees, 90 degrees, and then 180. So this is not spread out as much as possible. So a better way of drawing that would be to have, let's get rid of all this first. A better way of drawing that would be to have the fluorines at an angle so that you end up with 120 degrees between each of them. So this is the way that students in class would eventually get it to look. Now the CH4 is a little more complicated. If I spread them out as much as possible within two-dimensional space, it looks like this, with the bond angle of 90 degrees Celsius. And not Celsius, 90 degrees. And this is how almost everybody always makes the model the first time. But what's difficult to understand is that you actually have three-dimensional space to work with. So when you're able to spread them out completely, you end up with a bond angle of 109.5 degrees. Valence shell electron pair repulsion theory basically states that all the atoms and the bonds between the atoms want to be as far apart as possible. So they're going to spread out. Within the VSEPR model, a double or triple bond is no different in terms of repulsion than a single bond. So since they're all going in the same direction, you're not going to spread out a double or triple bond. They're going to stay together within the same direction. The different types of shapes that we're going to be talking about within VSEPR theory, they're connected to two different things: the bonding pairs and the lone pairs. It is incredibly important that you are able to draw correct Lewis dot diagrams for this unit, because based on the number of bonding pairs and lone pairs on that central atom, you'll just be able to look at a reference sheet to figure out what kind of shape you have. All right, let's look at some of the possibilities for when you have a central atom that doesn't have any lone pairs on it. In our first example here, we have beryllium hydride. Beryllium is an exception to the octet rule, whereas it doesn't always need to have 8 electrons around it when it becomes more stable. In this example, I have one bond on either side, so it actually only has 4 electrons around it, but this compound does occur. Because it's breaking the octet rule and you don't have any lone pairs or anything else on top, it stays as a straight line, and we call this a linear molecule. Carbon dioxide follows the octet rule, but it's the same idea. Because the double bonds are both going in single directions, they end up making a straight line. So this one would also be a linear molecule. Boron trifluoride is an exception to the octet rule. The boron currently has 2, 4, 6 electrons around it. When this happens, you have a bond angle of 120 degrees. So basically the same as one of the ones that we had made a couple slides back. And this one would be called trigonal planar. So if you have your reference sheet available to you, you would see that, okay, there are 3 bonds. There are 0 lone pairs on the boron, since that one is in the middle, and that's what tells us what shape we have. For methane, we have a carbon in the center with 4 bonds coming off of it. This would be called a tetrahedral. All right, let's see how things change when we start adding lone pairs. First up, we have ammonia, which is NH3. I have 3 bonds coming off of the nitrogen with the 3 hydrogens, and I have a single lone pair that's on top. So 3 bonds and 1 lone pair, that makes this shape trigonal pyramidal. And if we go back a second to the previous slide, the NH3 is actually part of the same family as this tetrahedral, because both have 4 things around them. And if you look at it, the NH3 is kind of like if you had just taken away this bond and you still had the remaining 3 on the bottom. So that bond would be right up here. But because there's a lone pair instead, this lone pair of electrons pushes down these 3 bonds so that they're no longer in a flat plane. Like in the situation we had with boron trifluoride, where you had 3 bonds and they completely spread out within the same plane. So lone pairs will force those bonds to go further down. Next up, we have water. This is a bent shape, but also part of that tetrahedral family, because there's 4 things around it. We have 2 bonds, which are going down, and we have 2 lone pairs on the top. All right, over here we have sulfur tetrafluoride. So we have 4 bonds coming off of that central atom, and we also have 1 lone pair. And with our final compound, we have bromine pentafluoride that has 5 bonds. Where's the cursor? We have 1, 2, 3, 4, 5, and the 1 lone pair. So this one's going to end up being square pyramidal. And this one is seesaw. So for your quiz, you're not going to have to memorize any of these names. You're just going to have to look off of your cheat sheet and see how many bonds in relation to how many lone pairs you have. And then you should be able to just go through the flow chart and figure out what you're going to have. All right, the relationship between lone pairs and bond angles. I mentioned before that all three of these compounds are part of the same family. They're part of the tetrahedral family because they have four things around them. So here I have four bonds, three bonds, and a lone pair right here. And this one is two bonds and two lone pairs. So as I start replacing bonds with lone pairs, the bond angle is going to be decreasing. This is due to the fact that the lone pairs are held more closely to the central atom than the bonds were. So you don't have to memorize the actual numbers here, but you should know that as you are going to increase the number of lone pairs, the bond angle itself is going to decrease. This is the cheat sheet that I've been referencing that you will be able to have on your quiz, and you should also have a printout of this from class. On the left side, we have the total number of electron groups. This is our bonding directions and our lone pairs added together. Then you have your bonding directions. So remember, a double bond would count as a single direction. So for example, if I had something like carbon dioxide, even though there are four total bonds here, there's only two directions. And then you have your lone pairs. So you can see that as you increase the number of electron groups, you'll have more possibilities within that family. The electron pair geometry is kind of like the family name, so it tells you all the main part that you could have. And then within that family, what happens if you start to remove bonds with lone pairs? You get different possible shapes. On the far right side, we have the potential shape that you could have in 3 dimensions, and you might have to draw these out on your quiz. The way that this works, if you have a regular straight line, that means that that bond is within the plane of your paper. If you have the dashed lines which look like they're going away from you, that means that it's going into the plane of the paper. If you have a darker line, which looks like it's coming out to a wider point at the end, that means that it is coming out at you. And that just helps to give it a little bit more of a 3-dimensional feel to it. Okay, this is the continuation of the sheet, so you can see what would happen if you had 5 or 6 electron groups. You might notice that a couple of the names actually start to repeat. So there's a few different ways that you could have a linear compound, such as the first example with 2 bonding directions and no lone pairs. Here the 3 lone pairs actually cancel each other out within their plane, or I could have 4 canceling out within their plane. So a few different possibilities to get the same shape. Alright, bonds polarity. This is a concept from our last unit. If you have 2 different elements that are covalently bonded together, they're probably going to end up making a polar bond. So an example of this could maybe be something like carbon to fluorine or hydrogen to oxygen. The 2 elements are going to have a different desire for electrons. So in this situation, the fluorine has a greater desire for electrons within a bond, and in this one, oxygen has a greater desire. So we call this electronegativity for a desire within a bond. The only time that you would have a nonpolar bond, so nonpolar, where they are actually 2 different elements, carbon to hydrogen. And this example you absolutely must know for your quiz. Any other time that it's a covalent bond and you have 2 different elements bonding together, you could consider it a polar interaction, meaning that the electrons within that shared bond are held a little more closely to one atom within the molecule as opposed to the other. Now, when we're actually drawing the polarity of the bonds inside the molecule, we have this symbol for partial. It looks kind of like a circle with a little tail on the end, and then we put a negative or plus sign. It's not a full plus or minus like an ionic bond, but it's a similar idea. From bond polarity, we can now talk about molecule polarity. A molecule could be polar if the polar bond inside of it is not canceled out due to symmetry. So let's look at a couple of different examples here. Here I have HCl. That is definitely a polar bond. Chlorine pulls on the electrons more than hydrogen would. This little arrow right here is pointing towards the element which is more electronegative, and then you put a line through the other end so it looks like a plus sign. So within this molecule, this would be the positive part and that would be the negative part. This molecule is not symmetrical. The H would not cancel out the Cl if I cut it down the center here. Therefore, this is going to remain a polar molecule. If I have NH3, because these bonds are not within the same plane, I have them not able to cancel out with one another. I also have a lone pair of electrons here up top. so this is going to remain polar. But if I have a similar compound like BF3, this also has 3 bonds going around the central atom, but because there's no lone pair, the bonds are not forced out of the same plane. And since these 3 bonds are pulling in equal and opposite directions at an angle of 120 degrees, then they are equally canceling out, and even though you have 3 polar bonds, it's a nonpolar molecule overall. The same exact thing is happening over here with CCl4. These are all equal and opposite directions that they are pulling in, bond angle of 109.5 degrees. And because they're all the same atom, they are equally canceling out. It's completely symmetrical. Here I had the same shape. Both of these are tetrahedrals, but in this one, chlorine would not cancel out with hydrogens on the bottom. So this ends up being polar. All right, finally, within an electric field, if I have a positive and negative end, anything that's polar inside of that field will align itself to maximize the opposite opposing attractions. So here, since oxygen, this pinkish part, is negative, it's going to align itself so that it's facing towards the positive end of this field. Whereas the hydrogen part, which is positive, will face the negative end. All right, another important concept within this unit is the concept of like dissolves like. This basically means that polar things like to be with other polar things, and nonpolar things like to be with nonpolar things. So I'm sure you know of the example of where you pour some kind of oil within a cup of water or a beaker of water, and they form different layers. The reason why they're forming different layers is that water is a very polar molecule. You have oxygen bonding to hydrogen, and because of the lone pairs forcing the bonds out of line, you end up with an asymmetrical molecule, so very polar. The oil, which has hydrocarbons, they are very nonpolar, so they do not want to mix together. Whereas if I have 2 polar things mixing together, like in this example here, they will evenly mix and be attracted to one another. Atomic forces. This is something that we talked about much earlier in the year, but we didn't really get into details of the specific types of intra versus intermolecular forces that you can have. Now that we've talked about bonding, we know that intramolecular forces could be ionic, covalent, or metallic. So these are the 3 types of bonds that we've talked about, and they are bonds inside of a molecule. It's what holds a molecule together as a whole. Intermolecular forces are the attraction felt between molecules that hold them together within a solid, liquid, or gas phase. So in the example here with hydrochloric acid, or HCl, the covalent bond between the H and the Cl is an intramolecular force. Whereas in the type of attraction between the 2 HCl's that holds them together within, say, a liquid phase, that would be an intermolecular force. Today we're going to be learning about the different types of intermolecular forces that you can have. The most basic one is London dispersion forces. This is the weakest out of all the forces, and it also occurs within all molecules, no matter what, even if they're nonpolar. A lot of times we draw a Bohr model or some kind of model of the atom where the electrons are evenly spread out, orbiting around the center of the atom. But that's rarely the case. The electrons are moving around really quickly, and at any given point in time, if you took a snapshot of that atom, there could be more electrons on one side of the atom as opposed to the other. This leads to an unsymmetrical or unequal distribution, and the side which has more electrons on it would be partially negative, and the side with less electrons would be partially positive. And whenever you have that opposing charge of positive and negative, it will cause things to be attracted to one another. So let's say that within this Cl2, we have a partial negative and a partial positive. Well, if in the molecule next to it, this one forms a partial positive and this one forms a partial negative, then these 2 molecules will be attracted to one another. This data table right here illustrates the connection between the number of electrons and the amount of London dispersion forces that are felt. So here we have 4 molecules, since they are diatomic, all within the same family on the periodic table. So these are all halogens. And as I increase the number of electrons going down that group, you can see that the melting and boiling points both increase. And melting and boiling points are basically just a measure of how much heat energy it takes to pull these molecules away from one another. How much energy does it take to go from a solid to a liquid or a liquid to a gas phase? So as I increase the number of electrons, it's getting harder to separate these things. That's because this unequal distribution is becoming greater and greater as there's more potential electrons to be on one side as opposed to the other. So as I go down that group on the periodic table, I'm more likely to end up with something that could be, say, a solid at room temperature. Our second van der Waals force, or type of intermolecular force, would be a dipole interaction. This also results in partial negative and partial positive charges due to different desires within the molecule. So if I look at the electronegativity for sulfur compared to hydrogen, sulfur has a much greater desire for electrons. So the electrons are pulled closer to that part of the molecule, partial negative, partial positive, and you have the same kind of attraction as you did for the London dispersion forces. The main difference between this and what we saw 2 slides back with the Cl is that this is a temporary dipole. So because the electrons are constantly moving around the atom or the molecule, you're going to have different dipole moments where maybe it flips and the negative is on the other side, or maybe for some fraction of amount of time they're exactly equal. Whereas in a dipole interaction, these have permanent dipoles. So the sulfur will always be the negative end and the hydrogen will always be the positive end. Because the fact that these are permanent interactions and the fact that it's just stronger, it's going to be something that helps to keep these molecules together better than London dispersion forces. All right, finally we have hydrogen bonding. This is really the same exact thing as a dipole interaction. It's just a lot stronger. And it only occurs when you have one of 3 elements connected to the hydrogen: nitrogen, oxygen, and fluorine, the 3 most electronegative elements on the periodic table. Because they have such a strong desire for electrons, and because hydrogen only has the 1 electron that it would not really give up, but that would be held closer to the oxygen within this bond, it makes hydrogen that much more positive and the electronegative atom that much more negative. So it's just kind of an extreme version of that dipole that we were just talking about, and that makes it a little bit stronger than a regular dipole interaction. Now it's worth noting that even though hydrogen bonding is the strongest of the intermolecular forces, and even though bond is right inside of the name, it's only 5% the strength of a covalent bond. So compared to our intramolecular forces like ionic, covalent, metallic, hydrogen bonding is extremely weak. And I encourage you to really not let that bonding part give you any kind of misunderstanding. Because even though it's called a bond, it's not really a bond. And just because it says hydrogen bonding doesn't mean that anytime you have a compound where hydrogen bonds, doesn't mean that that has hydrogen bonding. So for example, here we have methane, which is CH4. Methane does not have hydrogen bonding. Even though you have carbon bonding to hydrogen, it is not electronegative enough to make that force happen. All right, we're going to close things out here talking about hybrid orbitals. And this is going to be connected to what we talked about within quantum theory. So based on orbital notation for carbon, we would have 1s electrons going up and down, then 2s up and down, and then 2p x, y, and z spinning up in the x and the y orbitals. The z1 remains empty. But based on this picture, it looks like carbon can only form 2 bonds because there's only 2 unpaired electrons here. When we've been drawing the dot diagrams, I've been having you spread out those electrons as much as possible so you could tell, oh yeah, carbon has 4 potential bonding sites or 4 areas for atoms to come in and bond. So to make carbon more able to bond, you're going to take this 1 electron from this 2s orbital and promote it to the 2p orbital over here. When you do that, you'll have 4 unpaired electrons, which is the potential for 4 bonds. But this still isn't quite right, because the s orbitals and p orbitals, if you remember, the s orbital looks like a sphere. The p orbitals, we have the x-axis, the y-axis, and then the z-axis coming out at you, they're not really in favorable positions to bond with four things and spread them out as much as possible as we would need for a tetrahedral. So here we can see that those bonds have to be spread out in just the right way. So instead of remaining in 2s and 2p orbitals, we're going to end up making hybrids. The first hybrid is sp3. What I liken this to is taking your 2s orbital and each of your 2p orbitals, so we have 2px, 2py, and 2pz, and you put them all in a blender. And you mix them together evenly, and you get these four new orbitals that have some characteristics from the s orbital and the remaining characteristics from the 3p orbitals that went into the blender. These four lobes can spread out as much as possible to give you that tetrahedral shape that we're used to when you have four bonds. Since one s orbital and 3p orbitals went into the blender, that means that you can have a potential of four bonds, and we call it sp3 hybridization. So this is the way that you can remember how many bonds an sp3 orbital can be responsible for. If you think of the superscript of the s as an implied 1, 1 plus 3 means 4 potential bonding directions. Next we have sp2 hybridization. This would be an example like BF3, where boron starts with 2s2 and then 2p1. It needs to promote that bottom electron, the spin down electron, to the 2p orbital. So you have 3 potential bonding electrons now. The 2s orbital combines with the 2px and 2py. So these 3 orbitals are now going into the blender. And since the 2pz orbital was empty, that isn't part of it. We end up with 2 sp2 orbitals, and we have our 3 potential bonding directions. Now, if this was a different kind of situation where maybe I had something like this molecule right here, where I have 3 directions but I need an additional bond, that's where this orbital will come into play. So this 2pz, which did not hybridize, it could potentially go into a double bond, which we will talk about later. Finally, we have sp hybridization. So this would be if you had 2 bonding directions. So for example, I could take electrons from the 2s orbital, promote one of them to the 2p. Since these are not favorable for bonding, they blend together and they make 2 sp orbitals, one going along the one side of the x-axis, the other going along the other side of the x-axis, and you end up with a linear molecule. Now I also showed you that carbon dioxide could be linear earlier, so just like I mentioned before, the first bond will occur within these hybrid orbitals. The second one would occur between the 2p orbitals that did not go through the hybridization process. Alright, so the 2 different types of bonds that you can have within the hybridization process. You can have a sigma bond. This occurs when the bonds are actually directly overlapping, like in this example right here. So they overlap end over end, and because of that, they are the stronger of the 2 potential types of bonds that you can have. If you have a second bond that you need to make between the same 2 atoms, that would have to be a pi bond. These bonds are above and below the original axis. So here I have carbon double bonding to carbon with 4 hydrogens coming off of them. So the carbon will go through sp2 hybridization, so s plus the 2p's, so that's a total of 3. So I have 3 sigma bonds, or 3 direct overlaps, but then the carbon still needs to make that second bond. So from the original p orbitals that were not being used before, we get a pi bond, where there's some electron density that is shared above and below the axis. Here we can see how all this kind of fits together. So we have our direct overlap, we also have our indirect overlap. Now if you remember from way back in the beginning when we were talking about the different amounts of bond dissociation energy, I mentioned that if you had 2 single bonds, it would be about 700 kilojoules per mole, but what we actually get is around 657. So the second bond must be weaker. And that's exactly what we're looking at here. the pi bond, since it's not actually directly overlapping with the orbitals, it's going to be weaker than the original bond. All right, that's the conclusion of the notes for VSEPR. A couple of helpful videos that you might want to watch. The VSEPR theory videos by Tyler DeWitt, they were assigned on Kia, so if you didn't already complete those, make sure that you do so. There's a video that you could watch from TED-Ed, What is the Shape of a Molecule? And if you have a general understanding of orbitals and VSEPR and you kind of understand what's going on already, but you just want a little bit of extra review, then you can check out the crash course video, which is on the YouTube channel. The reading for the sections are 8.1 to 8.15 in the online textbook.